Welcome back to the channel. This is the first video in this current series of electrical demonstrations on the Classic Chrysler Mopar electrical systems. We did some videos last year, got into some details on some of this. We're going to go back over it again with another attempt at this fixture that hopefully is a little more clear and shows things a little bit better. In this video, we're going to stick with the stock as original stock charging system. No alterations, no attempts to fix things or to shunt wire, bypass things. This is the way it was. This is the way it was built when they were new. Pretty common across all the platforms from the early 60s through mid 70s. The basic charging and load distribution or power distribution system was the same. It starts with the battery. The battery is one of two power sources for an automotive electrical system. Generally, the main purpose of the battery is obviously to start the car, and it takes quite a bit of current to do that. So those automotive batteries have quite a bit of current potential in them, upwards of a couple hundred amps. This wiring, should a short occur, is not going to handle that kind of current without lighting up, basically. We're going to talk a little bit about circuit protection, what was designed into this, and with that, we're going to stick with what we refer to as unfused wiring. There are no individual fuses for these wires we're looking at here. The only protection we have here against overcurrent or short would be the fusible link out near the starter relay with a direct link over to the battery. And should a short happen in any of this wiring, or for that matter any of the components that are supplied from this wiring, example would be an ignition switch, internal short in there, something to do with the wiring to the ignition switch, it somehow touched the body, we're going to have a lot of current flowing here, so we have to have a way to stop it. The main distribution point in this system for power is splice 1. It's referred to as a welded splice. The wires are literally welded together, wrapped in friction tape, and then it winds up inside the harness. This is the point where all the loads of the car draw power. The fuse box, unswitched and switched at the fuse box, all gets its power from splice 1. Ignition switch is fed from splice 1. Ignition 1 circuits, ignition 2, all this stuff comes from splice 1. All original stock factory loads are taking power off of this splice. So when the car is at rest, engine not running, ignition off, the main power source is going to be the battery. If we turn on loads, again for this particular video, we're going to stick with the stock loads. We're going to turn the headlights on. We haven't started the car yet. That power is drawing from the battery. You can see the current flow on the ammeter over here, roughly 6 amps for those low beam headlights, those halogen sealed beams. If we kick it on the high beams, we're going to pull some more current. That's about 13 amps being drawn from the battery with the engine off. You'll see it on the dash mounted ammeter, letting you know that the battery is being discharged and at what rate. If we shut that off, you'll see the ammeter return back to a centered position. A centered position indicates there's no current flowing or very little current flowing. Let's go ahead and start the car up. In this case, we're going to power up the ignition system, assuming that the engine is running and we have some RPM happening at the alternator. The alternator is producing current now. You'll see that there's roughly almost 6 amps of current being pulled from the alternator at this moment. Where is that current going? Nothing is on. It's recharging the battery. It's headed back over towards the battery when we sat there and had the lights on a minute ago. That should be short-lived. It doesn't take long for the battery to return back to a full state of charge. You'll see it dropping. And when the battery establishes that, this particular style of battery, AGMs, fully charged, roughly 1/10 of an amp. And it won't be enough to even register on the ammeter. You can see just a tad bit of a charge indication on there now. Because the alternator operates at 1.5 volts, 2 volts higher than battery voltage, when it's operating, it becomes the primary power source for the car. Battery is no longer providing that power. It's coming from the alternator. Okay, we've had the ignition system powered up for a few minutes here. The battery should be pretty close to being full charge. I see like 0.2 of an amp going on over there, charging, headed into the battery. Another couple of tenths being consumed by indicator lights and such powered up here. Let's go ahead and turn the lights back on again with the alternator functional. We're still on high beam here, so we measured, 13, 14 amps here being drawn from the battery with the car off, no alternator functioning. We now see that current is coming from the alternator, and there's no current coming from the battery as it should be. With the ammeter in series between the power distribution point, splice 1, and the battery, this is indicating no current is flowing. During normal, healthy operating conditions while the car is in use, the battery is good, alternator is able to keep up with whatever the car is consuming, we should see no current indicated here. It should be close to being centered, if not centered exactly. That's how the system was designed to function originally. If there was a problem in the battery, a cell is becoming sulfated or something is changing in the battery. The batteries from that time, lead acid batteries, weren't really designed, well, I take that back. It's not that they were designed to fail. They failed relatively quickly. If you got a couple, 3 years out of a lead acid battery back in that time, you did pretty well. But they usually would start to indicate abnormal charging rates prior to a complete failure. And if you're paying attention to your ammeter indication while you're using your car, you might be able to save yourself from a dead in the water experience from a dead battery. If it starts showing abnormal charging current, I would go get the battery checked out, see if it passes load testing. If not, get a new battery in there. It might save you some heartache. Anyhow, that's how the system normally works. Any loads you place, anything you turn on the car, let's just, I showed you the wipers there a second ago, or excuse me, in the first video. Again, there's no mechanical load on the motor, so we're not going to pull a lot of extra current, but we're up a couple of 3 amps from the alternator. and alternators keeping up with it. And I should also mention too, one thing I can't emulate with this power supply as far as an alternator stand-in is that alternator is not able to produce its full capacity at low RPMs, idle RPMs. So you're going to see in the real world, alternator is going to produce much less than what the total capacity of the alternator is at idle. You have to get some engine RPM going to get full capacity out of that alternator. And speaking of capacity, these alternators from this time period, 35 amps maybe would be its maximum output. Some AC cars got a little bit larger alternators, but we didn't see really large alternators for another few years yet. We'll get into some of that discussion in some of the other videos coming up, how to increase the capacity of the alternator and things that might be necessary to support that. But I just wanted to go back over how the system was designed to function. Engine off, no alternator output. The battery is the primary power for this system. Engine running, alternator in operation. The alternator is the primary power source for this. Has to do with where the current comes from. So let's talk about circuit protection. It's important. The term simply means to be able to cut off current to a particular wire circuit in the event of an overcurrent situation, a short. There's different types of circuit protection devices. And not all of what you're seeing here was available back then. None of this blade stuff was around back in the early 60s and 70s for automotive use. It was either a glass fuse, very simply a little glass tube with a filament of some kind through it, through each end cap. They were available in various amperage ratings. There was a couple different configurations on size. This wouldn't be automotive from that time period, but later on we saw some of that. And circuit breakers, resetting circuit breakers. These would have been used. Power windows, a power top maybe. On like a station wagon, a rear liftgate window motor would have been wired through something like this. These are auto resetting. If it senses an overcurrent situation, it'll open, but then it will attempt to close again after a few minutes. After it cools off, it attempts to close again and reset. There was some others that came along later for a blade type, but again, we weren't using blade type stuff back in the 60s and 70s. There were also fusible links used on these cars, mainly right at the battery to protect the larger wiring. And as we indicated a minute ago over at the fixture, quite a bit of that wiring is depending on this fusible link to protect that wiring from dead shorts. A fusible link is used in the engine compartments usually because they tend to be more reliable than fuses, and they can absorb some current spikes that the system may produce. Where a fuse would snap immediately and open up. One thing to keep in mind about a Mopar fusible link, or that particular circuit protection, if this opens and the car is in motion, you have a stall. The car will die. And we don't want this to open up unless it's absolutely necessary. This actually takes a little bit of time at This actually takes a little bit of time to heat up before it opens up, so on a dead short it should open, but we don't want that to fail. One of the things about fuses, they tend to be sensitive to shock and vibration. In an automotive application, they tended to fail. Whether or not there was an overcurrent situation or not, I've seen many of these open up internally at the end cap, still be intact through the filament, but we don't want to use that for sensitive circuits such as this, where there would be an engine stall resulting if this should fail. Some these days like to promote the use of more modern maxi fuses, and the blade type stuff on this application. I don't do that. There's nothing wrong with fusible links. Another thing to keep in mind about automotive electrical systems from this time period was that a lot of this electrical connections and terminations were not sealed against moisture or weatherproofed in any way, and the engine compartment was usually exposed to quite a bit of moisture. We developed corrosion problems on electrical terminals under the hood, and it's gonna lead to other issues. This is also true of the connectors. Other connectors that were used in automobiles from that time period. I mentioned Packard terminals. Basically, it's a spade, more commonly known as a spade terminal. These are generic aftermarket quarter-inch spade terminals, male and female. Packards were very similar to that, but these were designed to snap into insulators. A bulkhead insulator, for instance. There were also individuals, or six-way. I mean, they were used throughout these cars, but none of this stuff was sealed in any way, shape, or form, as pretty much everything is today. You look at electrical connectors in cars today, and each one of them has a little seal, and the way it's designed to keep these guys dry. These cars were never meant to last long. And something to keep in mind as we're looking at electrical issues on these cars, where when these cars were being built, they were designed to last 3, 4, 5 years until the next trade-in. That's it. 100,000 miles, that car was worn out. And you went and traded it in and got another one. And these weren't designed to last any longer than that. Today it's kind of expected that cars last longer, and the cars are built differently now. In any event, these Packard connections, and we're going to get into a little more detail on that. If you haven't seen some of the other videos, I did talk about some of these guys, but these have been a source of problem, especially when significant current is supposed to flow through them. This is an original female Packard from a bulkhead connector. This is the battery feed. Very obviously there's some heat going on here, and you'll notice that the heat just kind of worked its way along the wire from the terminal. No other heat damage on the rest of the wire. That indicates that this is the source of the heat. The heat started here and worked its way down. It's also common to find there's some more heat damage going on here on this wire. This guy is the battery feed. The black one is the one that runs out to the alternator. We'll talk a little more about why that guy is a little more fried than the red one is, but this is common, and this was doing this kind of stuff when they were new, and especially on cars that had a lot of extra electrical options, more factory loads. Well, I'll get into that a little bit later when we talk about where the current's flowing. But these guys are a problem, and they weren't sealed. There was an attempt to keep dirt and dust out of the whole thing in general, but this is not weatherproof in any way, shape, or form. I probably forgot to mention that fusible links come in various sizes. The stock fusible link was typically a 16 gauge, 5 to 6 inches in length. We don't want to get too much longer than that because it just adds unnecessary voltage drop to the whole circuit. 12 gauge, this would be for some modifications. We'll talk more about that in a minute, but we want to size these about 4 gauge numbers smaller than the wiring it's designed to protect. We'll talk about that in a minute. While we're looking at terminals, let's talk about the other common terminal type you'll find in these cars. This is a brand name Molex. In their design, they come in different. There's a smaller one and a bigger one. You're going to find these on the ignition switch Molex connectors, and you're going to find them on the turn signal connectors, the smaller ones, male and female, pin and sockets basically. These were also extensively used, unfortunately, in some circuits that were designed to handle some current, and these guys couldn't hold up. I did a whole video on the Molex connector for the ignition switch. You may want to check on that. But these are kind of common as well, the Packards and the Molexes. That about covers the basics, I believe.